last time we had talked about magnetic dipoles. And we said that a current loop is a magnetic dipole. So if you have a loop of current, I'll draw it this way, where this is the axis going through the loop, and the loop is such that the conventional current is coming out towards us at the top, and we'll draw it so the conventional current is going into the board at the bottom of this loop. Then this produces a dipole pattern of magnetic field, and the direction is going to be this way. So along the axis, we get the field pointing that way. On the perpendicular axis, just field points in the opposite direction. And then it kind of curls around as you go to other observation locations. And so this is a pattern you should just recognize and know that current loop produces a dipole field. And you should be able to work out the direction. It's, surprise, surprise, another right-hand rule, right, where you can say that if you, well, a couple different ways. If you can figure out the direction of the magnetic field at the center of the loop, then you know it everywhere along that center line axis, okay? And so you can do that whatever way you like. But another rule that actually works, if you want to memorize another one, is that if you curl the fingers around in the direction of the current, the thumb points in the direction of the field through the center, okay? But if you could also say, well, if I look at it head on, we could use the usual cross product and say that if the current's going like that, and I want to find the direction of the magnetic field at the center, then again, I delta L cross R hat, thumb points out, and once you have the field in the center, you know the field direction everywhere along that center line axis for a dipole. It just works out that way. Okay. Question? Okay. So we worked this out. We found a formula for this. So the magnetic field of a loop we're talking about on that center axis, okay, on the axis that goes through the center of the loop. And that magnitude was mu naught over 4 pi 2 times the current in the loop times pi r squared over z squared plus r squared to the 3 halves. And if the z being this distance, right, the z being the distance from the center to some observation location along that center line. And if z is much greater than the radius of the loop, then this simplifies to mu naught over 4 pi, and we have 2 times the current times pi r squared over the distance cubed. Okay, so we get a 1 over distance cubed dependence. It's a dipole, okay, just like we saw for electric dipoles, or 1 over distance cubed dependence. We also introduced at the very end last time magnetic dipole moment. We use the symbol mu, Greek letter mu, without the little sub-zero, okay, so it's a different quantity. And it's defined to be, for a single loop, just the current times the area. So for a circular loop, the area is pi r squared. So we could rewrite this as mu naught over 4 pi 2 mu over z cubed, just combining the current and the area into a single quantity.